Hello, this is my final. So my name is Austin Chan, and it's my final for Data 605. So for this first problem, it says to use R to generate a random variable x that has 10,000 random uniform numbers from 1 to n, where n can be any number of your choosing greater than or equal to 6. And then generate random variable y that has 10,000 random normal numbers with a mean of mu is equal to sigma is equal to n plus 1 over 2. So what I did here is I set a seed so that every time I run this code I get the same result, and I just put in random uniform, so 10,000 values from 1 to 6, and then I did an R norm for y for 10,000 iterations with n plus 1, so 6 plus 1 over 2 for both the mean and the standard deviation. So parts 1, A, B, and C are to calculate as a minimum the below probabilities A through C. Assume the small letter x is estimated as the median of x and the small letter y is the first quartile of y. Interpret the meaning of the probability. So the first one we have here, probability that x is greater than the median and that it is also greater than the first quartile for y. So the way that I found this probability was I just took the number of values in x that were greater than the median, and then also the number of values in x that were greater than the first quantile in y over the total number of values of x values that were greater than the first quantile of y, and that gave me 0.5127. So the next probability is the probability that x is greater than the median and that y is greater than the first quartile. So to find that, all you need to do is take the individual probabilities of x being greater than its median and y being greater than its first quartile and just multiply them together. So kind of by definition, a median will have like greater than 50% of the total number of values, and then the first quartile will be 25%. So multiplying those two together will give you 0.375. But so I did a more explicit version here, and it comes to the same number. So the next probability is the probability that x is less than the median and that x is greater than the first quartile of y. So this one's a little bit different from the part A, where instead I flip these signs right here. So instead of being greater than, I put less than, and then also I put that x has to be greater than the quantile of y. So that's what this is, given that x is greater than the first quantile of y. So that comes out to be about 0.487. Alright, and then so part 1D, investigate whether the probability of x is greater than the median and the probability of y is greater than the first quartile is equal to just those two probabilities multiplied together. So for this one, I built a table that calculates the marginal and joint probabilities. The first lines of code here find the number of observations for each joint probability, and then the next few lines calculate the marginal probabilities by just adding them together. So right here we could see that, and then I would just label their names and then put them into a table right here. So x is greater than the median and y is greater than the first quartile. It'll have like this percentage of all the simulated values that satisfy those requirements, and then also the margins as well. So according to that table, the probability that x is greater than the median and y is greater than the first quartile is 0.3755, and the expected probability is 0.375, which is fairly close. And since it's so close, it's hard to say that these two variables are dependent on each other because its behavior exhibits independence of the two variables. So I'd say that these two probabilities are equal. So using Fisher's exact test and the chi-square test to kind of put more of a formal testing for this, let's see. So I took, so I made a matrix of the counts for each of these categories, and I just put them in a little table here, and then I ran a Fisher's test on it, and the Fisher's test gave me a p-value of 0.834, which is very large. When a p-value is large for the Fisher test, that means that it's probably not statistically significant, in that the distributions or the counts are probably due to random chance rather than having a significant relationship. And so I also ran the chi-square test on it as well, and has a similar p-value of 0.835. So right here and right here, so they both come to the same conclusion that these tests, or that these two variables do not exhibit behavior that would suggest that they are dependent, given that their counts are so close to the expected values if they were random. So yeah, and then here's some more language about the definition of the Fisher's exact test, and then also the chi-squared test, which I don't want to necessarily read right now, but you can go in and read it. So problem 2, the Kaggle regression techniques. So the first thing I did here was just load them from my working directory, and then load the train and the test set. And so this first question asked me to provide the univariate descriptive statistics and appropriate plots for the data set. So there were 81 variables in this data set, so I didn't want to plot all of them, as that would really clutter the PDF. So instead I just made a little function here that returns a 5-number summary for numerical variables, and then also a table of counts for the categorical variables. So here we can see for this M subclass variable, we have like the minimum, first quartile, median, mean, third quartile, and maximum. And I did this for every single variable. And then for variables that were categorical, like the street, whether it's like gravel or pavement, I set it so that it'll just count the number of each category. So right now there's like 6 houses that had gravel on the street, and like 1,454 houses that had pavement on the street. And so this just goes through every single one. Nothing super interesting necessarily. So I'm just going to scroll through the rest of these. Yeah, so the next problem was to find a scatter plot matrix. So I loaded a package called Coregram, which creates these nice correlation matrix plots. So instead of having, I guess, the individual correlation values, you can put in different graphics instead. So I decided on this bottom half I would have the plots of the variables. Plots of this one is the sale price plotted with lot frontage, and then this plot is a M subclass versus plot frontage, and it'll have the plot here. And then in this top right corner I have the correlations displayed as kind of a color scheme. So this blue means that there's a positive correlation, and like the deeper the color, the higher the correlation is. So this kind of is a neat little visual way of displaying correlation matrix. So here I made the same matrix. Let's see. Oh no, this matrix is slightly different. Instead of M subclass, lot frontage, and sale price, I picked lot area, overall quality, and overall condition, and then use the core function from R to make a correlation matrix. And then so I put that here. And then hypothesis testing. So the next thing I did was I checked, or I guess checked if these correlations were significant. of the correlation between these three variables relative to the sale price. And it looks like this test has a really low p-value, so it's statistically significant. And here we have the 80% confidence interval, so it's between 0.232 and 0.294 for lot area. And then I did the same thing for overall quality. Instead, this correlation is a lot higher, so it's a 0.79. The p-value is also very low, so that's a good sign that this variable is statistically significant. So right here, the 80% confidence interval is a 0.77 to 0.8. And then I did the same thing for the overall condition relative to the sale price. And this one, the p-value is low, but compared to these where it's basically 0, this one is a 0.002, which is a little bit more suspect. So technically it is statistically significant, but the value is like much closer to 0 than the other two, which leads me to think that since this statistical significance may be due to just large sample size rather than actual significance. So it might be important to watch out for this here. And then, yeah, so through this analysis, I was able to find a couple things. In the first part, I looked at descriptive statistics with a 5-number summary and the table of counts for each category. I made some correlation matrices using the CoreGram package and found a few interesting relationships between sale price and M subclass and lot frontage. So then I looked at 3 different or other variables: lot area, overall condition, overall quality, and I checked the correlations using the correlation test relative to the sale price, and then I found that overall quality looked like a pretty good predictor, but with lot area and overall condition, it's lesser so. Alright, and so with the family-wise error, given that the confidence of the test is so low, so like normally you have a confidence level of like 0.05, so like 95% confidence interval, but this one was at 80%, so that gives you like a 20% chance of type 1 error for each test that you do, which is already like incredibly high. And the more tests that you do, the higher this family-wise error gets. So in this case, we only did 3 tests, but the chance of family-wise error is above like 48%. Kind of the way that we normally get around this is you'd maybe do something like the Bonferroni correction, where you set your p-value threshold to be much like higher, so that instead of doing like 80%, you probably have to be like 99.999%, so that the chance of a type 1 error is like much lower. So yeah, so I'd be concerned here for family-wise error. So then in here it says to invert the correlation matrix, so I just use the solve function and it just inverts it for you. And then it says multiply the correlation matrix by the precision matrix, so I just took the matrix that I just solved for here and then multiplied them together, and it just gives me the identity, and then I flipped it again and it gave me the identity again. So then conduct LU decomposition, so I basically just took the function that I used in my homework too for the LU decomposition and then just plopped it in here. So I have this function here called row reducer, which basically converts a matrix to like reduced row echelon form. So we can take a closer look here. Yeah, and then I have this LU function which actually does the decomposition using this row reducer function. So all of this row reducer function does is that it just converts a matrix to reduced row echelon form, and then this decomposition parses that form out into the lower and upper matrix. So then I did that, and then here I have the initial matrix, and then the L and U, and then again the initial matrix. So yeah, and then many times it makes sense to fit a closed form distribution. Select a variable training that is skewed to the right, shifted so that it's above 0. Okay, so I chose MS subclass for my variable. It looks like this, has a pretty heavy right skew. So then it says to load the mass function and then fit it to a exponential density function. So I did that here with this, called this fit distribution function, and it gave me this value. And then I plugged that back in as lambda to get a sample, and I did 1,000 of those samples, and then plotted that here, so we get a nice little histogram of the samples. But relative to, so relative to that, whoops, looks like I picked the wrong thing. So here I actually meant to put lot area, but so if I look at the histogram of a lot area and the histogram of the samples, it's very clearly different, where this lot area is much more centered around here, and it tapers off significantly relative to this, where it's much more gradual. Let's see, so here I calculated the quantiles. It looks like for the 5th and 95th percentiles right now, it looks like 533 and like 30,500. And then the 95% confidence interval, assuming normality. So what I did is I simulated a normal distribution with the same parameters. So just taking the mean and standard deviation of the lot area and then simulating it for however many observations there are. And so putting that into a confidence interval, I get this negative 6,000 and 27,000, which doesn't really make sense because you can't have a lot area that's like less than 0. And so then I looked at the actual data itself, and it looks like the confidence interval is 3,300 to 17,400. So the initial data had a very clear right skew, so it didn't make sense to assume normality with it. The refit exponential distribution was much closer to the true distribution than the normal. And so since the normal was negative, that didn't really make sense when the minimum value is actually 1,300. But the normal's confidence interval had an upper bound that was closer to the true upper bound compared to the exponential distribution. So, but overall, the exponential distribution was a better fit. Yeah. So build a multiple regression data and provide a model summary. So in terms of fitting the data, this was a pretty involved step where I had to clean the data and like interpolate any missing values. So I loaded this mice package, which is a package that helps you interpolate values, and then this SQLDF function, which allows you to run SQL in R. So right now I just made a nice little SQL query that helps me clean the data, where like some of these ordinal variables I set them to like 1, 2, and 3 if they were ordinal, and then here there's like qualities like excellent, good, and average, and I set them all like 5, 4, 3, 2, 1, so that when I put them through the linear model, it's able to recognize that it's ordinal and treat them kind of numerically instead of having to treat them as categorical variables. So I did that for all of the ordinal variables. And yeah. So then afterwards I imputed the missing data, and this mice function uses a predictive mean matching to impute the data where it's missing, and so this kind of goes to the iterations, and then from there that imputes all of the numerical data. So any value that was like missing in the numerical data, it got imputed with the mean matching, and then all of the categorical data that was otherwise missing, I just assigned to 0, so that the model will still fit and not exclude any rows. So fitting the model. So generally, when determining house price, the things that I've been told are most important were the location of the house, like the neighborhood or the street that it's on, and then how physically large the house is. So the variables that I used were related to kind of those two things. So right here I have the neighborhood, which will indicate, like, I guess, which neighborhoods those houses were in. Being like more affluent neighborhoods will have more expensive houses, regardless of, I guess, the size and condition of the house. But otherwise, I picked a lot of variables that are related to the actual size of the house. So stuff like garage areas, if you have a big garage, the lot area, like how big the actual size of the land that you're buying, total number of rooms that are above ground, these kind of things. And then a few other variables that I found were statistically significant, like a basement exposure and overall quality. So right now I have this summary of the model right here. As we can see, a lot of the variables are statistically significant. One thing I noticed with the neighborhoods is that the only neighborhoods that are statistically significant look to be the expensive neighborhoods. So if you live in an expensive neighborhood, the value of your house will go up a lot. But if you live anywhere else, it doesn't really seem to change the house price very much. So I thought that was interesting. So then after I fit the model, I ran some residual analysis. So looking at this residual plot, looks really clean. There's no discernible pattern that I can see. The variation as the index increases is about the same. There's a few outliers, but relative to the total number of values in this data set, they're not particularly influential in changing the fit. So pretty tight spread. And yeah, so overall this looks pretty good. So in terms of the normality, we can look at a QQ plot. We can see that almost all the points follow the line fairly closely, except at the tails where it kind of deviates. And so, it's possible that there might be a variable that affects houses that are appraised significantly low or significantly high in price, but otherwise it's a pretty good fit. And the residuals look normal, so it indicates that their linear fit is a good fit. So after I fit that, I wanted to squeeze a little bit more predictive power out of my model, so I ran it through some cross-validation. So I used this Caret library, which contains a lot of useful machine learning functions, and then I ran a 20-fold cross-validation with the model that I used here, and then so put it through the training, trained it across 20, and then it came out with this new model, which has a slightly higher R-squared, slightly lower error values, so it's tuned a little bit better. So then with the prediction, I ran the same cleaning script as I did on the training on the test. So here's just the same SQL code, basically, then the same imputation, and then from there, so I changed this, the other missing values to 0, and then I ran this predict function to make the prediction, and then here they are right here. So then, so you can look up my Kaggle username. It's AUChan, and then my score is 0.21546. So thank you.